An isobaric process is any process that takes place at a constant pressure. Let us consider a gas that is placed under a constant pressure P1. This can be done by placing the gas in a piston cylinder arrangement. The piston exerts a constant force on the gas that is equal to the weight of the piston. Since the area of the piston is constant, and pressure is equal to force divided by area, then the pressure exerted by the piston on the gas is also constant. The shown two-dimensional pressure versus temperature plot on the left is a projection of the three-dimensional phase diagram on a plane that is perpendicular to the specific volume axis. The constant pressure P1 that is acting on the substance in our experiment is represented by a plane that is perpendicular to the p-axis and intersects the p-axis at pressure value P1. The value of P1 is between the pressure at the critical point and the pressure at the triple line. On the two-dimensional plot, the constant pressure P1 is depicted by the shown line that is perpendicular to the t-axis. Next, let's study what will happen if we cool this gas by reducing its temperature while keeping the pressure constant. Starting from the shown point, in the gas region of the phase diagram, which is depicted by the white circle in the 2D plot, and the white sphere in the 3D plot. As the gaseous substance cools down in an isobaric process, it changes from a gas to a vapor. In a subsequent section we will discuss the difference between a gas and a vapor. Then at this point, liquid starts to form. Notice on the 3D phase diagram, how the sphere, which depicts the condition of the substance, is now moving within the liquid-vapor region. When the liquid is first formed, the substance develops a meniscus or surface. The meniscus separates the liquid on the bottom from the vapor on the top. As the latent heat of vaporization is extracted from the substance at constant temperature, the substance gradually changes to a pure liquid. At the shown point on the 2D and 3D phase diagram, it is a pure liquid. Of course, since the liquid phase is much denser than the vapor phase, it occupies a much smaller volume than the volume that was originally occupied by the vapor. And as you just saw, the piston moved down a very large amount, indicating that the specific volume of the substance decreased a lot. In other words, since the density is equal to 1 over the specific volume, as the substance cools down at constant pressure, its specific volume decreases, and its density increases. As the liquid is cooled further, its specific volume decreases even more. Then when the temperature reaches this point, a solid starts to form, and the substance enters the solid-liquid phase region. Notice how the substance in the piston cylinder arrangement first forms a surface that separates the solid at the bottom from the liquid at the top. Then as the latent heat of fusion is extracted from the substance at constant temperature, the substance gradually changes to a pure solid. At the shown point it is a pure solid. Of course, since this substance contracts on freezing, the solid occupies a smaller volume than the volume that was occupied by the liquid. Cooling the solid phase further results in a pure solid that is at a lower temperature and a lower specific volume. You can now drag the slider or the piston itself to change the condition of the substance, and observe how that affects the 2D and 3D phase diagrams and the piston cylinder simulation. When you wish to continue with the lecture, press the play button at the very top. The opposite of the process we just described with the cooling of a gas to form a solid, can be performed by heating a solid to form a gas. In this case, if the pressure is the same, the heating process will follow the same intersection curve as the cooling process we just described. The intersection curve is, as we have described before, between a constant pressure plane and the three-dimensional phase diagram. The only difference will be that the process will be moving in the opposite direction. Hence the specific volume of the substance will increase as the solid is heated, Then the solid will start to melt at constant temperature, by turning into a solid-liquid mixture. Eventually, as the heating continues, the substance becomes a pure liquid. Then further heating results in the formation of vapor. The substance remains a liquid-vapor mixture, at constant temperature, until the liquid completely evaporates after it has absorbed the latent heat of vaporization. After the substance becomes a pure vapor, further heating continues to increase the vapor's specific volume. An isothermal process is any process that takes place at a constant temperature. Let's consider a vapor that is undergoing isothermal compression, at a temperature that is between the critical point and the triple line. This can be achieved by placing an uninsulated piston cylinder arrangement inside the large tank containing a liquid that is maintained at the desired temperature. The large liquid tank acts as a heat sink that maintains a constant temperature for the fluid inside the piston cylinder arrangement. As the vapor in the cylinder is slowly compressed by the piston, it will tend to heat up, but heat flow to the heat sink surrounding the piston cylinder arrangement will keep the temperature of the fluid that is in the cylinder nearly constant. As the vapor that is inside the cylinder is compressed, its pressure increases, as we can see with the two-dimensional isotherm, as well as with the three-dimensional intersection curve of the constant temperature plane. With the surface of the phase diagram, during isothermal vapor compression, when the pressure reaches this point, the vapor begins to condense. As the vapor turns to liquid, the heat of vaporization is lost to the liquid that is in the heat sink tank. This process continues at constant pressure until we reach this point on the phase diagram, where all the vapor has turned into liquid. If the isothermal compression continues, the pressure in the liquid will continue to rise, albeit at a steeper slope than in the vapor, since the liquid is less compressible than the vapor. When this pressure on the phase diagram is reached, the liquid starts to freeze. As the liquid turns to solid, the heat of fusion is lost to the liquid that is in the heat sink tank. This process continues at constant pressure until we reach this point on the phase diagram where all the liquid has turned into solid. Further compression of the solid phase increases the pressure in the solid at an even steeper slope than in the liquid, since the solid is less compressible than the liquid. You can now drag the slider or the piston itself to change the condition of the substance, and observe how it affects the 2D and 3D phase diagrams and the piston cylinder simulation. When you wish to continue with the lecture, press the play button at the very top. The reverse of the isothermal process we have just described can occur if we lower the pressure that is acting on the solid phase that is within the piston cylinder arrangement, while keeping the temperature constant. In this case, if the temperature is the same, the expansion process will follow the same intersection curve as the compression process we just described. The intersection curve is, as we have described before, between a constant temperature plane and the three-dimensional phase diagram. The only difference will be that the process will be moving in the opposite direction. As the pressure is decreased, the solid first expands, and then it melts and turns into a solid-liquid mixture. The specific volume increases at constant pressure as the solid turns into a liquid. After all the solid is gone, as the pressure is lowered, the liquid expands. At this point, the liquid begins to vaporize. The vaporization process continues at constant pressure while the specific volume increases, and the fluid in the piston cylinder arrangement absorbs the heat of vaporization from the liquid that is in the heat sink tank. Finally, at this point, all the liquid has turned into vapor. Further expansion decreases the pressure of the vapor while increasing its specific volume.